Hi, my name is Zoey Todd. I'm a senior at Clarkson University, and my project is on radiation detection using TADF molecules. The motivation behind this project is to aid in the development of spectroscopic plastics. Spectroscopic plastics can be used in radiation portal monitors that enable the identification of radioactive material, not just the detection of a radioactive material. We want to move beyond asking, is there a radioactive source, to what is the radioactive source? There is evidence that suggests that TADF molecules can help to answer our question. TADF stands for thermally activated delayed fluorescence. Why did we choose to use TADF molecules? We chose TADF molecules because their wavelength of emission matched the sensitivity of the photodetectors and currently utilized radiation portal monitors. They have the ability to convert non-emissive triplet states to the excited singlet states easily at room temperature. Therefore, they are predicted to emit more light upon exposure to a gamma radiation source. The more light that a scintillator emits, the better that material is for scintillating-based radiation detection. Approach. The Gaussian 16 software package was used to predict the properties of 6 classes of TADF molecules. To this end, we performed geometry optimizations of each molecule's ground state, as well as the first singlet and triplet excited states. Density functional theory is a well-established computational tool used to study a molecule's electronic structure. DFT can thus provide a means of determining which TADF molecules should more quickly convert from the excited triplet state to the excited singlet state based on the difference in energy between those states. Methods. Optimized ground state geometries were computed at the B3LYP-D3BJ/G or 6-31G star basis set level of theory in the gas phase at room temperature. These structures were then used as a starting point for geometry optimizations of the lowest 3 singlet and triplet excited states. Excited state geometry optimization also inherently include calculations of the energy barriers, which are measured in electron volts, between the ground state and the excited states in question. And we used the CAM B3LYP-D3BJ/6-31G star level of theory for all of the excited state computations. The first molecule that was submitted for optimization is 2CZPN. And below we can see that each one of these energy levels is the amount of electron volts it took to go from the ground state to the first singlet state, the second singlet state, and the third singlet state. Same thing with the triplet, just first triplet state, second triplet state, third triplet state. So in these, what we're looking for is the difference. The difference between the singlet and triplet states is what can tell us the relative stability about these molecules. And we expect to see a higher energy as the number gets bigger because it takes more energy to go from the ground state to the third excited state than the ground state to the first excited state. The next molecule that was submitted for optimization was 46DCZ-ppm. This is what it looks like here on the right. The same thing, we're noticing that it does take more energy to get from the ground state to the first, or to the second and the third prior than the first. Same thing with the triplet. We're noticing that the number of electron volts is getting higher as we're seeing first, second, and third excited states. Next was submitted DMAC-DPS. This is what the molecule looks like to the right. Again, we are noticing that in this molecule, the jump in electron volts is a lot higher. We go from 2.9 from the first excited state to 3.6 in the second excited state. and then to a 4.2 in the third excited state. This molecule is undergoing a reoptimization because in the triplet state, it is showing that we are getting a negative value for electron volts, which just means that the molecule did not correctly optimize. Next, we submitted DMAC, TRZ, this TATF molecule. We can also see that the singlet, it increased the electron voltage and increased 1, 2, and 3. In the triplet, we noticed that it took, and the same thing in the triplet, it got larger from 1 to 3. SITRZCZ2 was the next molecule submitted. And we are noticing that this molecule is also reoptimizing because some of the values, as you can see, it took more energy to go from ground to the second excited state rather than more energy to go from the ground to the triplet or the third excited state, excuse me. The triplet does seem to have optimized correctly. They are increasing as you go down. And finally, TRIS-PZZ, it is also shown here on the right, was optimized, and we can see that it did get bigger as you go from ground to first to second and to third in both scenarios, singlet and triplet. So we are looking to see the energy difference between the singlet and the triplet excited states so that it can tell us the stability and whether it has the smallest energy difference between itself and the ground state is the most stable excited state. So in these cases of these molecules, the triplet state for all of the molecules, for example, 2CZ-PN, the triplet is only preferred by 0.2 EV. So now what we hope to do is to vary the structure of these molecules and see how it affects the excited state energies. What I learned how to use a terminal and a command line interface and how to navigate Texas A&M's high performance computing clusters. I had never used a terminal or a command line prior to this REU. I learned how to set up aliases. I learned how to submit a job to Gaussian. I learned how to modify scripts so that certain jobs can be submitted. And I learned how to extract the needed data from a Gaussian output file. All of those values did come from a Gaussian output file. Future research. Since we have the data from the ground, excited singlet and excited triplet states, we can now vary the structure of these molecules to see the effect on the excited state energies. To that end, we are presently conducting a Hamlet study investigating what effect, if any, the electron withdrawing cyno and electron donating methyl oxyl substitutes will have on the excited state energies. With that being said, we ran 12 more of the molecules. The 6 that I showed before, each added a cyno and a methyl oxyl substitutes, and it will help to aid in the conclusion of the question, electron withdrawing groups on this molecule, does it cause the singlet electric excited state to be lower in energy? Acknowledgements. I would like to acknowledge Dr. Amanda Graff, my mentor of Los Alamos National Laboratory, and Dr. Jordan Harper of Los Alamos National Laboratory for their assistance on this project.